There is a mountainside in Alaska that is moving, not eroding the way all mountains slowly do. Moving, sliding, as a single enormous mass, a whole face of the mountain creeping downhill toward the water below it, tracked by instruments bolted to the rock that measure its progress in millimeters. Scientists are not wondering whether this slope will fail. They are wondering when. And here is the number that made them break protocol and warn the public directly. If that slope lets go all at once, if the entire mass drops into the fjord beneath it in a single catastrophic collapse, the water it shoves out of the way could climb the opposite wall of the fjord to a height of around 1,500 feet. 1,500 feet. Higher than the Empire State Building. A wall of water taller than almost anything human beings have ever built, thrown up a mountainside by a landslide, in a remote corner of Prince William Sound. Your first instinct is that this cannot be real, that a wave that size belongs in a disaster film, not a geology report. But that is the detail that tells the real story here. And it is the reason scientists are not treating this as a hypothetical, because it has already happened. Twice, once in living memory, and once within the last year, in the same state, a few hundred miles away. The tallest wave ever recorded on Earth was a wave exactly like this one. And the mountain in the fjord is not doing anything new. It is doing something Alaska has done before, and the only thing anyone is missing is the date. So let us walk through what is actually happening up there, because every piece of it is more unsettling than the last. The slope in question sits in a place called Barry Arm, a narrow glacial fjord in the northern reaches of Prince William Sound. About 30 miles by water from the small town of Whittier, Alaska, it is beautiful country. Steep gray rock walls, deep cold water, tidewater glaciers calving into the sea. In summer, it is full of tour boats and cruise ships and kayakers who come to see the ice. And along one wall of that fjord, there is a slab of mountain roughly half a cubic kilometre in volume. The main body of moving rock has been estimated at around 455 million cubic meters, and worst-case modeling has considered volumes as large as 680 million. Numbers that size are almost impossible to picture, so hold it this way: it is not a boulder, and it is not a rockfall. It is a piece of mountain large enough that if it entered the water quickly, it would move the sea itself. The obvious question is why? Why is a mountainside that presumably stood in place for thousands of years suddenly sliding now? The answer is the ice. Specifically, a tidewater glacier called the Barry Glacier, which used to fill the fjord directly beneath that slope. For as long as the glacier was there, it did something invisible but essential. It pressed against the base of the mountainside. A glacier that thick is not just ice sitting in a valley. It is a colossal buttress, a wall of frozen mass leaning against the rock, holding the slope in place from below the way a hand braces a leaning bookshelf. As long as the ice was there, the mountain could not move, because there was nowhere for it to go. Then the glacier retreated. The fjord below the landslide was occupied by the Barry Glacier until around 2012, and as the ice thinned and pulled back, the buttress that had held the slope for centuries simply melted away. The hand came off the bookshelf, and the mountainside, no longer supported at its base, began to do the only thing gravity was ever going to let it do. It began to slide toward the empty water where the ice used to be. This is the part that lifts the story out of the textbook and into the present. That retreat, that loss of supporting ice, is happening right now, across Alaska, in fjord after fjord, as the glaciers pull back. Barry Arm is not a freak. It is the first clear example of a hazard that is multiplying. In 2020, the changes at Barry Arm alarmed an interdisciplinary team of scientists so badly that they did something scientists are usually reluctant to do. They went public before all the research was finished. They wrote an open letter, warning that a catastrophic collapse of the slope could generate a tsunami large enough to send a potentially fatal wave toward Whittier, and toward the hundreds of tourists, fishing vessels, and hunters who might be in the sound at any given moment. Their timeline was stark. They believed it was possible the landslide-generated tsunami would happen within the next year, and likely within 20. To understand why a landslide can produce a wave that dwarfs anything the open ocean makes, you have to understand that this kind of tsunami is a completely different animal from the kind most people picture. The tsunami everyone knows is the one made by an undersea earthquake. The seafloor lurches, a broad pulse of water spreads out across an entire ocean, and it travels for thousands of miles, arriving on distant coastlines hours later. Those waves are wide, fast, and, crucially, they give warning. There is time. There are systems. A landslide tsunami is the opposite in almost every way. It is not spread across an ocean. It is a violent, local, near instantaneous act of displacement. Imagine dropping a brick into a full bathtub. The water does not gently rise. It leaps, all at once, straight up and outward, splashing over the rim in the first instant. Now scale the brick up to half a cubic kilometre of solid rock, and the bathtub up to a deep glacial fjord, and you have the mechanism. Millions of tons of mountain hit deep water at high speed and punch the water out of the way. It has nowhere to go but up. That is why the run-up can reach heights that sound invented. Right at the point of impact, the water is not forming a traveling wave yet. It is being thrown, bodily, up the nearest solid surface, which in a narrow fjord is the wall on the other side. The modeling for Barry Arm found that in the worst-case scenario, wave heights right at the slide could exceed 200 meters, over 650 feet, and the run-up on the opposite fjord wall could exceed 500 meters. That is where the 1,500-foot figure comes from. Not a wave rolling across the sound. A vertical wall of displaced water climbing the rock face directly across from where the mountain fell in. And if that still sounds impossible, here is the proof. From the summer of 1958. On the night of July 9th, 1958, a magnitude 7.8 earthquake struck the Fairweather Fault in the Alaska Panhandle. The shaking loosened about 40 million cubic yards of rock high on a cliff above a T-shaped fjord called Lituya Bay. And that massive rock, some 90 million tons of it, dropped from an altitude of roughly 3,000 feet straight down into the water of a narrow inlet at the head of the bay. What happened next was recorded, measured, and is not in dispute. The displaced water surged up the slope directly across the inlet and stripped it clean, not damaged. Stripped, it tore away every tree, every root, every scrap of soil, all the way down to bare bedrock. And when a United States Geological Survey scientist named Don Miller later measured the trim line, the sharp boundary between the forest that survived and the mountainside scoured to rock, he put its height at 1,720 feet. 1,720 feet. Higher than the Empire State Building. It remains, to this day, the tallest wave ever recorded anywhere on the planet. And there were people in the bay that night. There were 3 fishing boats anchored in Lituya Bay when the wave came. One was lost with the 2 people aboard. But on another boat was a fisherman named Howard Ulrich and his 7-year-old son. They felt the earthquake. They saw the wall of water coming down the bay toward them, and there was nothing they could do but hold on. The wave picked their boat up. It carried them up and over on a wall of water higher than the trees, and then it set them back down, and against every reasonable expectation. They survived. A man and a child lifted over a forest by the sea and alive to describe it. Don Miller, studying the bay afterward, found something else that should stay with you. There were older trim lines, fainter scars from earlier waves at lower heights from years and decades before. Lituya Bay had done this again and again over the centuries. It was not a one-time catastrophe. It was a pattern written into the mountainsides that almost no one had been reading. Now, if you are tempted to file all of this under history, under something that happened once in 1958 and makes a good story, here is the fact that should change your mind. It happened again in 2026. In the spring of that year, scientists confirmed that a landslide generated tsunami in a fjord called Tracy Arm in southeast Alaska had reached a height of 1,580 feet, the second highest such wave ever measured, just short of Lituya Bay itself. Not in a textbook, not in the distant past. Now, in a remote fjord, a mountainside let go, and the water climbed to within 150 feet of the world record. And most of the world never even heard about it because there was no town in the way. This is the through line, and it is the reason Barry Arm matters. Across Alaska, the glaciers are retreating, and as they go, they are unbracing slope after slope that stood for thousands of years while the ice held them. Every steep fjord where a glacier is pulling back is a place where the hand is coming off the bookshelf. Barry Arm is simply the one that happens to have a town, a monitoring program, and a name people know. The wave in Tracy Arm is what Barry Arm looks like when nobody is watching. But here is where accuracy matters most, and where the honest version of this story is both more precise and, in a strange way, more chilling than the headline. That 1,500-foot number is what happens at the slide, right there in the fjord at the moment of impact against the opposite wall. It is not what would arrive at the town of Whittier, 30 miles away, because a wave that begins as a vertical wall of displaced rock and water does not stay that tall as it travels. It spreads. It loses height with every mile, and by the time it crossed the 30 miles of Prince William Sound to reach Whittier, the modeling shows it would be a very different thing. Whittier is a strange and vulnerable little place to begin with. A town of a couple hundred people, most of whom live under a single roof in one 14-story building. Reached from the outside world through a single one-lane tunnel bored through a mountain. When scientists first ran the numbers in 2020, they estimated a 30-foot wave could reach that town. But after a year of on-site monitoring and far better data on the shape of the seafloor and the slide, the United States Geological Survey revised the worst-case estimate downward, substantially. The refined modeling put the wave arriving at Whittier at around 7 feet, roughly 2 meters, reaching the town about 20 minutes after the slide. 7 feet is not 1,500. That revision matters, and any honest telling has to say it plainly. The town itself, in the current worst-case science, faces a serious but survivable wave, not a biblical one. But do not let that number comfort you too much, because it hides where the real danger lives. The killing zone is not the town. It is the water near the slide. In Barry Arm itself, in Harriman Fjord, in Port Wells and College Fjord, waves over 5 meters could arrive within 10 to 15 minutes, and right at the slide, the water climbs those walls. And those are exactly the places, in exactly the season, where the tour boats idle in front of the glaciers, where the cruise ships bring their passengers to the ice, where kayakers paddle and fishing vessels work. Potentially hundreds of people at once, on the water, looking at the very glacier whose retreat is driving the whole disaster. For them, there is no 30-mile head start. There is no 20 minutes. There is a mountain, and then there is a wall of water, and almost nothing in between. Which is why the last piece of this story is a race against a clock nobody can read. Barry Arm is now one of the most closely watched slopes on Earth. There are instruments on the rock and in the water, measuring the creep of the mountain and waiting for the signature of a sudden collapse. And the Alaska Earthquake Center, led in this work by the state seismologist Mike West, has built something that did not exist before. A landslide detection system able to identify a slide and the tsunami it might generate within minutes of it beginning. It is the first system of its kind in the United States, and it grew directly out of the monitoring at Barry Arm. But detection is not prevention. The system can tell you the mountain has fallen. It cannot stop it, and it cannot give back the minutes that a person in the fjord does not have. The most it can offer is a warning, sent into a place where, near the slide. A warning and the wave arrive almost together. So picture it, right now, Tonight, out in Barry Arm, in the dark, a sensor bolted to the rock is registering the mountain's slow creep downhill, a few millimeters closer to the water than it was last month. The slope is still moving. It has not stopped since the ice let go. Across the fjord, the wall it would climb stands silent. The same kind of wall that in Lituya Bay was scraped to bare bedrock at 1,700 feet. The same kind that in Tracy Arm was scoured this year to within touching distance of the record. Somewhere out on the Sound, when summer comes back, a tour boat will idle in front of the glacier, engines low, and every camera aboard will be pointed at the ice. The mountain has done this before. The mountain will do it again. And the one question every instrument on that slope is built to answer, the only question that actually matters, is the